In this session, we are going to study the speed of waves using the dimension analysis. So we are going to use a dimension analysis. In the dimension analysis, we just examine the dimensions and find the equations for the physical quantity we'd like to find. So in this case, we'd like to find the speed of waves using dimension analysis. So at first, we'd like to find out the dimensions of the speed of our waves. So to describe the dimensions, we use these symbols. So V, dimension of the V is a meter per second. So at first, we'd like to find out physical quantity related to strings. So we could consider two dimensions of the force. If you consider the strings, is pulled by the force of F. So force is one of the quantities you could consider. The dimension of the force is newtons. This is Newton. Newton is using the MKS unit, kilogram, meter per square second. This is the dimension of the newtons. And also the other quantities. Another quantities we can consider is mass per unit length. We could consider the total amount of mass of our strings, but we don't know the length of the strings. It's better to consider the mass per unit length. You can take a unit length of our strings, and then how much mass is it? The mu. Mu is a mass per unit length, like a density. And the dimension of the mass per unit length, kilogram per meters. This is a unit of the mass per unit length. And then by looking at these two dimensions, you could consider the F over mu is a kilogram, meter per second squares over kilogram per meters. Then kilogram is going to be cancelled out. This becomes meter square over second squares. So if you look at these two units, it's very similar. If you take a square root, it becomes equal to the V. So finally, we could find out these equations. B equals square root F over mu. By just considering the dimension of each physical quantity, we could derive another physical quantity. So in this case, the V is expressed as a function of the tension force and the mass per unit length. This is the speed of the waves can be obtained by considering the dimension analysis. Then we'd like to move to the next topic of the wave equation. So in this case, we just consider the sinusoidal waves. At first, we'd like to consider the specific case of the wave functions. Then, what kind of the equations can be satisfied by this wave function? So, as a test trial function, we consider sinusoidal waves. Y equals A cosine kx minus omega t. Then, the particle velocity can be obtained using the derivative. So derivative with cosine becomes a minus sign. So this we should have a minus sign. Then this is a derivative. We should use a chain rule. So and then minus omega times minus becomes a positive. So it becomes omega capital A sine kx minus omega t. So if you take a first derivative with respect to t, partial derivatives, it becomes omega A sine kx minus omega t. And the accelerations can be calculated using the second derivatives. This is second derivative. One more derivatives. So in this case, the derivative of sine functions becomes cosine. So this is becomes just positive. And then one more derivative from the minus omega. It appears here. So this becomes a minus omega squares. A cosine kx minus omega t. Then you can look at these formulas here. then it becomes minus omega square y. So acceleration can be expressed minus omega square times y. Then on the other hand, we could calculate the slope of these wave functions. So slope can be calculated, just derivatives. Find the derivative round y with respect to x. So in this case, the derivative cosine becomes a minus sign. And derivative of the kx becomes, you have a k. And the second derivative, you can apply the curvatures. To find the curvatures, we need to find the second derivative with respect to x. Then one more derivative becomes minus k square y. So by looking at these two equations, second derivative with respect to t, and by looking at these two, is very similar. But this is multiplied of the omega squares. This is the k squares. So if you draw the 1 over omega squares round square y, second derivatives, round t square, equal 1 over k squares, second derivative of y with respect to x. So this is second derivative with respect to t is omega square over k squares round square y round x squares. And this is equal to the wave speed, v squares. Then we have a wave equation to describe the motion of the waves. This is second order partial differential equation. This is a wave equation. But we don't use the general formulas for the wave. We just only consider the simple case of the waveforms. So maybe it's better to consider the more general case. Using the equation of motion, we'd like to derive the wave equations. So in this situation, we consider this xy coordinate. At first, we those y coordinate and x coordinate. At first, strings is on the x-axis. This is strings. Then we consider the sections of the strings. It's a very small region of the strings. This is x and x plus dx. So mass of this element is m equal mu times dx. If you multiply the mu times the length, you will have a mass of this element. And in this case, the position of the element, this element, remains horizontally. The position of the element remains horizontally. Then we could consider that this strings is moving up to the new positions. The new position of the strings. But in this situation, this element doesn't move in the horizontal direction. So the force, acting force, in the horizontal directions have to be the same. So we said this is F. Capital F is acting on the both end of this string element. This F is same. This is the total F. Then horizontal component. This is F sub y x plus dx. Then this is F sub y x. Okay, and then these two F as an equal amount of the forces acting of this element, because this element doesn't move in the horizontal directions. Then we would like to write an equation of motions. Equation of motions. The mass is expressed mu dx. This is mass times accelerations. This is acceleration, like a acceleration. And the force acting on this element is F sub y x plus dx. This is a positive force minus F sub y x. The difference. One of the end is moving, pulling to the upward directions, and the other end, the acting force is directed toward the downward directions. Then this part is a force, net force. Then you can write under these equations. So you can apply the Taylor series expansions. This forms. It becomes round F sub y round x dx. Okay. And then also from these triangles you can find out F sub y over f is a F sub y f is a correspond to the slope of these curves. So slope of these curves is equal to the round y round x. So for the F sub y's you can substitute here. Then it becomes round x f round y round x dx, and f is constant. Then and also dx appears in the both sides. So mu dx second derivatives. Dx appears in both sides. Should be cancelled out. And f is a constant value. We can move the outside of these derivatives. So equations. Finally, it becomes round second derivatives equal f over mu and the second derivatives with respect to x. Okay, so we derived the wave equations. So in this situation, we just only use the equation of the motions for the Newton's laws, and then find out the wave equations of the strings. Okay, this is the end of this sections.